Right, so I'm fine with just pseudocode. That's cool, but definitely try to implement that. But try to pseudocode first before you actually code. Write your pseudocode and then write the code. So you're solving it twice, sure, right? And also, it's a good practice because there was a lot of feedback that we got from those people called volunteers that said that people didn't seem to do a lot of pseudocode. Okay? Any questions on what I'm looking for today? All right. So the first problem we are going to do is this leak code problem, which I'm putting in the chat. I will also throw it in our channel. This problem on a scale of 1 to 10 in difficulty should be somewhere around a 3 at this point for you. If it's not, more practice. But based off of that, we will only be in breakout rooms for about 10 minutes. Okay? So let's just create breakout rooms. Just gonna make sure things are okay. Okay, I will open the rooms for 10 minutes on this one. Okay? See you all later. I guess it's mostly the words. Yeah, let's go over it. Let's kind of bang it out. Well, this was one way to write it. Okay, so right, the wording, reading these problems is definitely, part of it, right? It's part of the challenge and getting used to it, trying to really figure out what am I trying to get, right? Like I've got these J that represent stones and that are jewels, and I've got stones that I'm going to be given, and I have to find out how many stones that I have are also jewels. So I guess what that means is I have, and yeah, if you look at the output, yeah, it's a little weird. It's just, I guess we've got these stones and these are our jewels. And so we have to figure out how many of these stones are jewels, right? So anytime one of these is included in one of these, we can increase our count, right? So the first way we might think about doing this is we might start with having some kind of count, right? And we'd set that at 0. And then we might say like, all right, I'm going to iterate through my stones. So I'll say for let stone of S. So I don't care about the indices. And then I can just say, hey, if J dot includes stone, count plus plus, right? And then at the very end, I can go ahead and return my count. And I think this works. Let's check. We'll run that one. We'll submit and run the whole thing. Okay, and we go, all right, yeah, not bad. 80, this seems fine, right? For this kind of submission. How many people solved it like this with includes?
So Corey, quick question. What's the time complexity of that?
Well, that's what I'm going to ask you. What do you think? What do we think the time complexity of this is?
Well, I'm assuming that it's what's what n squared? But I don't know how includes works, so I don't know.
Okay.
O1. So I don't know.
Okay. So I'm getting a couple mixed. Henry, so a constant, that O of 1 is constant. So this definitely is a constant. If there's any kind of loop, we can't do a constant. That means no matter what size, it's always the same. That's like just straight math or lookup. But I'm seeing some linear stuff, and I'm seeing some n squared, right? So that it all kind of depends on what does this includes do, right? That's the question. What does this includes really do? Well, how would you write your own includes?
It'll be
I
some
would
kind of
probably be right.
iteration.
Compare it. Like compare the
Okay.
index.
That brings us to the next task. We are going to spend 5 minutes in the breakout group and write our own includes. Okay? And then we will continue going over this problem. All right, so task, I'll write it in the chat. Write your own includes method. So it can take in an array, or you could add it to the array prototype, which might be kind of cool. So, okay, we will go into our breakout rooms. We've got 5 minutes, so we're going to try to bang this one out. We're going to try to work on our speed today a bit. Solving problems fast can be important sometimes.
Oh,
All right, how did it go?
Well,
Good. Went really well.
Well, okay, let's see just how everybody did. Quick poll. Keep it open for 20 seconds.
I'm
All
also
right.
cool.
Nice. People are destroying this poll. Okay, awesome. Oh, I love the high participation on these. That's awesome. I will share the results. So we're living in 5s and 4s. The 3, I'd say that's pretty good for a 5 minutes working on a problem, right? I mean, that's not a lot of time. That's great. On this kind of problem level, I would probably rate the difficulty of this problem also around a 2 or 3. But I'm like doing that on like a really hard scale, right? I'm not just doing that on a light scale. All right, let's go over how we might write our includes. And if anyone else wrote it differently, let me know. But let's say we're writing, I've got a little practice thing open here, and I could just say const includes, and this takes in an array, and we'll say a target. Right, and because this array isn't sorted, we actually have to iterate through this, right? So we'll say for let element of array. Don't care about the indice in this sense, and I'll say, hey, if my element is equal to target, I'm just going to go ahead and return true. Otherwise, at the very end of this function, I will return false because it's safe to say we did not find it. So let's go ahead and try this. So we'll console log some array, and we'll make a target of 3.
question, Cole.
Yes.
So dot includes can only be used for an arrays. That's an array method.
I believe. So
I don't know.
yeah.
Okay, so we can't dot include.
No, it's also a string method.
Strings might, yeah, strings might have it. Jay says they do. I
Just
believe.
open strings with the jewels and stones, right?
Yes,
Yeah,
do
yeah,
some
yeah,
strings,
Yeah, that is true. Yeah. Okay.
Okay. Well. All right. Let's see what happens. So the way we wrote this is true. I think this will also work. The way we wrote it, I think, is flexible enough to do a string. Like, well, that would look for an individual character. I'm not invoking it correctly. So we have our true there. We can put a capital L. This should give us back false because it's case sensitive. All right, so it works for strings too. We wrote this in kind of a flexible way. But what's the time complexity of this?
Linear.
Yeah, this is linear, right?
Yeah.
What?
Yeah, it's linear.
Okay, so if this is linear.
So I have a question.
Okay.
Like when I looked at how the MBN does it, they just use index of, because you'll get a -1 if it's not there.
Right.
Is that basically just a loop too?
Yep, that's exactly the same. It's just we would care about the indice and just return the indice or return -1 here.
Got it.
It's the same. right? I mean, if we really want to make a true includes, we could also like add it by doing like string dot prototype dot my includes. Remember these? Function target. And then we would take all this code.
Oh, prototypes.
Do we remember any of this?
Yeah.
Yes.
Not really.
Right? These are just prototypes. We can add our own methods onto things. So this would be, instead of this, I would say of this. And then this would work in the same way, but instead of calling includes like that, I could just say, I could have my string, like let's say I'll make a string, be hello. I could just call string dot my includes and check like, hey, does it include this lowercase l, right? So this allows me to call things method style. Capital L should be false, and it works as well, right? So these are two different ways to write it includes. This is a bit more to real life, right? This is how the real includes is working. This is referring to the string that includes is being called now. Okay. Anyway, so if includes is linear and
How, Corey?
hang on just a second. So if includes is linear and this for loop is linear, what's the time complexity overall?
Quadratic.
Sorry?
Quadratic.
Quadratic, right? More specifically, because these are two different strings, right? Because S is not the same string as J. So they could have different lengths. It is more precise to say M times N or N times M, where N is the length of one string and M is the length of the other. Does that make sense? Because there's no guarantee. If they were the same length, it would be N squared. But since we don't know if they're the same length, it's just N times M. But still quadratic. And yeah, somebody had a question. Sorry. What was it?
I was saying you put string dot prototype. What if it was an array? It would just be array dot prototype.
Yep, exactly. If I wanted to make this flexible for arrays, it would just be array.prototype.
And is there a one that is like universal?
Between the two? No. Thank God. I mean, I like it would be cool in this situation, but you could get so much like, it could be so messy in the sense that like they could behave differently. And like for this one, we were kind of lucky. I mean, the real includes works a little different for strings because I'm pretty sure, if I'm not mistaken, like I can say node and I can say hello dot includes and I can actually do like hello and this will give me back true. Right? So this is only doing a comparison of singular characters, while the real includes is doing like these groupings, but that's not how the includes works for arrays. Like I can't do the same thing, I don't think, where I can say 1, 2, 3 dot includes 2, 3. Like that doesn't work the same, right? So the includes really don't work identical. They only work if you're looking at like per element identical. So it's a good distinction to make. Okay, so we've got this, and this is, we said, kind of quadratic. And what's the space complexity of this?
Quadratic.
So the space complexity of this is constant. So that, you want to think of space complexity as the amount of extra space we require as our inputs grow to infinity. So like these are given, like this is not really counts as extra space. This is what the input is. So the only place that is including our space here is this count. But no matter what the size of J and S become, our count variable always is going to be taking up the same amount of space. We don't need more additional variables for the size of our inputs. So we can say that our space for this is constant. And you'll notice as you dissect more and more of these problems, there's often this trade-off between time complexity and space complexity. So like the faster the algorithm, you often end up using more space. While if you want to have like no extra space, constant space, you often write a slightly slower algorithm. Typically, it's preferred to write faster algorithms that use more space. Okay, so how could I speed this up? Does anybody have any suggestions? Sorry?
Can you? Nah, forget it.
Okay, well, what are you thinking?
Is there any way you can rewrite that if statement, maybe as some kind of ternary or something, or no, or is that not?
Well, we still have to check if J includes it, right?
Yeah.
Somehow. So what else could we do? Let's think about how we could store more information to better ourselves.
Well,
Use
you
object.
put the keyword create an object. I mean, create a class.
Yeah, right. So I heard object, right?
Yeah, object.
So I could have an object that could be keep track of my joules. Sure. So I have it. And what would I want to store in this?
The key. Well.
You loop through it to determine how many times the letter is.
Yeah.
Thank you.
Okay, so our joules are always going to be unique. I think that's within the problem because we don't actually care if they're in there multiple times. We just care that they're in there, right?
So
but we do need to loop through it.
So it'll be a key value pair. So it'll be the joules and the amount of times that the joules, like the count.
So I don't think we need a count because although like a lot of problems do require counts and they're good, but our joules, we don't really need this count of our joules because they're only going to show up as unique, right? And we're not decrementing joules based off stones. We're just checking to see if our joule has that like stone in its string. So instead we can just add the joule to our joules. And it feels weird because it feels like we should have a count, but really we don't need a count. We could just write true. And then we could say, hey, if joules at stone, so if the stone's actually a joule, then we can increment our count. And so this should also pass all the tests. So what's the time complexity of this now?
That is 01. 01.
Yeah, because I think it's 01 as well because I'm keying into an object is not constant time.
Yeah.
No, maybe it's linear.
So
iterating
this
in the
line
first
is
part.
constant,
Oh, yeah.
but we're still doing a couple of loops, right?
So it's still linear.
Right. So this is linear. This is specifically n plus m because we don't know if they're the same length. It's linear. You could get away with n, but if you really want to be precise, it's n plus m because we're doing a loop of each. And what's the space complexity of this?
Constant.
Constant. Oh.
So that means that no matter how
linear.
big this is, the size of things we're holding in memory never change. Is that true?
No, it's linear.
Not true.
It has to be linear, right? Because as J gets bigger, we'll have to hold more things in our joules. So because of that, it is linear. So So we have this kind of awkward true statement here that's really doesn't do anything, right? Is there a data structure that we know of that would be even better to use right now? And I will say Hasib did talk about it, and me as well.
You mean an abstract data structure?
Yeah, it's an abstract data type. All right, I am looking for a set, right? Because a set behaves very much like an object, but it doesn't have the values. It's essentially just storing the keys. So since we're not really doing anything with these values, we only care about the key. So I might as well just make a set. So I could just say my joules is equal to a new set, and I could pass in J. And then instead of saying brackets, I would say joules.has stone. And with just that minor change, this should also work. This is still technically n.
So as far as like the runtime, is that?
Are you saying about this thing?
Yeah, is that time complexity or is that just runtime?
It's like a mixture of both. It depends on your internet speed and your machine. It changes. This is a faster algorithm than what we wrote the first time, but it's saying it's slower, which is not true.
Yeah, that's what I was confused about.
So I wouldn't stress that. You'll see that 2 days ago, this is the same algorithm I wrote 2 days ago, and that one only took 48 milliseconds, while this last one took 60. So go figure. This one's probably like 100% faster, but it's the same code. So this is still linear time, or n plus m, and this is still linear space complexity. But this is the best answer that I can think of for this. I mean, we could make this, we could get fancy and make this one line.
So if it has the same speed and the same and takes up the same memory, how is it faster?
Yeah, that's what I was gonna ask.
This is not faster than the object one. It's not faster than the object one. This is the same. This is the same speed as the one with the object. Both of those are faster than the one with includes. This is just a little bit cleaner because why have an object if you have no use for the value? That's all. So sets are like, I'm just an object of keys. While objects are like, well, I can hold keys and values. What up, right? So kind of a dealer's choice, but set is the slightly more appropriate data structure to choose in this problem. Okay, cool. Let's go for another problem, shall we? Let me pull up my notes of problems. Okay, this is a cool problem. We are going to work on this linked list problem, which is posted in the chat and in our classroom channel. We will have, let's do 20 minutes to work on this. Please pseudocode this out first. And I don't know if I should give any hints. I think you'll be fine. Hints, you can think about pointers. It's like a loose hint. Okay, pointers. All right, let's go for 20. Breakout rooms. But pseudocode it first. All right. Wording. What was tough about this one?
I didn't think we had like a clear idea of like what we were like, what the question was asking, and also what the game plan was, and that really like stumped us because we were trying to figure out what each thing was. Okay, to be specific, there's this position argument, right? So we were trying to make sure like that was the right input. We were trying to make sure what defined a cycle. And I think that we were lost on whether or not we needed to iterate or not, or whether or not we needed to just check at that position to see if the dis.next at that pointed back to something else. So there was like a lot of variables, and we were just like, we couldn't think of a solid game plan.
Okay, cool. I will say that with linked list, right, we can't check a specific position if we're only given the head node. So you almost always are going to have to do some.
So the
sort
head
of
was
loop.
head was an array though. That's what was throwing things off. It was like it was an array. So you're like, isn't the head supposed to just represent the one node?
Yeah. So
Versus
that's a
array.
familiarity with a lead code thing. So it shows that input like it looks like an array, but really the node that what you're given in that function is just the head node.
And was 0 indexed the head?
Zero index. Sorry.
They were saying that something that represent the position.
It says that position was written as a 0 indexed. So we thought that position was just like, if it was positioned at 1, that was like an index of 1. That's all it really meant. That's what we were thinking.
I'm trying to take a look. Yeah, the 0th index is the head.
Okay.
Not array. Yeah, and you can treat it as such.
Yeah, and example 1 had an array full of 4 different things. So that's why it was like confusing.
So that's them showing you the entire list. So that's just, yeah, I get that. That's the more LeetCode problems you do. Same with like any of these coding environment like solving. That kind of stuff will become a little bit more easy because you'll have dealt with that. But yeah, that's an array that's representing the list, but you still can't see what each one points to unless you look at the drawing. So let's
quick
not.
question.
What?
In the drawing, right? So there was I forgot what it was, but there was something that was pointing to the head, which was 2, and then the tail was pointing to the head as well.
Right.
So the only reason what made it a cycle is the fact that the tail was pointing to the head and not the other node that was pointing to the head.
Right. So whatever makes it, so a cycle in a linked list is anywhere that has a loop. So if we were to iterate, we would never end because we have some loop here. I'll make that A, and this is B. Right, this is some list, and I have a C here, and like this is a directional, right? And maybe I have a D. Now my D could point anywhere, right? It could point to null, and we'd have a regular linked list, or like maybe my D points to B, and so when we iterate through this, we'd go like, oh, A dot next is B, B dot next is C, C dot next is D, D dot next is B, B dot next is C, dot next is D, dot next is B, and we end up in this loop of a cycle.
So that could be anywhere.
Question is about, right? It could be anywhere. So D could point to B, it could point, right? This could point to A. We'd have this whole loop, so the head keeps pointing all the way, and eventually the tail of this, well, there really isn't a tail, right? It's not, there's not actually a tail in this, right? Or, right, none of the cycles have a tail. That's important. Or we could, our D could point to our C right here, right?
So all we were doing was checking to see what pointed to the given position.
What pointed to the given position? What do you mean by that?
So they gave us, so were we supposed to use that position, that a position argument?
So we linked lists don't have a position argument. They only start with the head.
And that was it. Okay.
That was all we have. So the way this works is we can think of, well, how can we use two things? Because we need a way to break out, right? Because if this is a cycle, if our D points to our B here, back at our B, And we can't just iterate through because we'll never break out. Right? We'll just keep saying, while node to node.next equals, well, let node equal node.next, while node, node equal node.next, and it'll just keep going, and we'll never end. So we have to think of a way to break out. And
I
so
have a quick question.
Yeah.
If D points to A, how would we know what the head is?
If B points back to A, like
if
that
D,
instead?
If D points to A.
Oh, if D points to A. So if D were to point to A, like, that's like a philosophy question, Doug, right? How do you know who's the head? Yeah, you don't. You just go with whatever node you're given, I guess, in that regards.
So to break out of it, we would have to like keep track of how many times something may have pointed to the same thing, and then say like, well, it didn't point. It pointed to the same thing a few times, so it's time to break.
Okay, so that's a pretty cool answer, right? So Danny suggests us keeping track of like an object of some sort where, or maybe not an object, because I don't think that will work for like on nodes, but maybe it's a map, which essentially is the object. But like, so we go and we have some count of times we've visited. So we go, okay, we've got our A, we've visited one time. We've got our, and we move our pointer to the next one. We go, okay, we've got our B, it's been visited one time. Sorry. And we go, okay, well, we've got our C now. We move to C. C gets visited one time. And we keep moving. We go, okay, our D has now been visited. So our D's been visited one time. And our D goes now to our B. And we see, oh, we've already gotten a B. And since we've already gotten a B and we've repeated, we could just return true. Right? That could work.
Yeah.
What's the time complexity of that?
Linear.
Yeah, that's linear. And what is the space complexity of this?
Constant.
Constant.
So you guys, constant means that no matter the size of the input, we won't be holding any more information.
Linear, yeah,
Linear.
Yeah.
Right? It's the same definition as time, essentially, just with space.
Okay.
Yeah, so this is going to be linear, right? Because as this grows, we'll have to have more information in here, always. So that makes it linear. Okay. Cool.
So in this instance, you're storing the value.
I guess I'm storing the value in this one, or maybe I'm storing the node ID if I can, or just the node itself.
Question.
Because if we have C, if we have like a longer list and C repeats itself, we wouldn't know whether or not it visited the first C or the second C.
That's
right?
true. That's a negative. I'm getting poked by a screw on this whiteboard. I guess it used to be put into a wall. But yes, that is a negative, right? If we have duplicates in our data, we'll end up getting potentially false positives if we're keeping the keys as the value. Oh, great. Now the screw's on the floor somewhere. Okay. Hang on. I found it. I bet you didn't know I was going to come out on that side. Okay. But yeah, you could also, but each node should have a unique ID as well. So potentially you could use that. And I think there's different data structures that handle that key value mapping a little bit better. Like a map object, I believe, can hold that better. But it behaves very much like an object. That said, is there a better way? Is there a way that takes linear time, but instead uses constant space? And the answer to that is yes, there is. And that's where the hint came in as the pointers, plural, right? So what if we had two pointers? We had a pointer here. You can't see that. We have a pointer here at our A. and we also have another pointer here. So our green is going to be a runner. All right. Our green likes to run because green is mean and mean people run away after they're mean to you. While our blue, who's feeling blue after the green was mean, right? Our blue is the walker. It walks away in sadness, right? So we've got our runner and our walker. So the runner runs twice as fast as the walker. Okay, so let's see what would happen with that. So if we were in some kind of while loop and we said, okay, our walker is going to take a step. So our walker takes one step and ends up at B. And our runner is going to take two steps and end up at C. Okay, let's continue this pattern. So now our walker takes one step. And our runner has to take two steps. So from C to B. Okay, now our walker takes one step. And our runner takes two steps. Now they've met. So when one thing is going at the pace of 2 and another thing is going at the pace of 1, how could they ever meet?
If there's a
Common
cycle.
multiple.
Right. They can only meet if there's a cycle.
Yeah.
Right? Because if there's no cycle, the runner will always get to the end first. And if there is a cycle, once they both enter the cycle, eventually they will land on the same node. That's just a mathematical fact. If the one thing is moving at 2 and the other one is moving at 1, eventually they will converge. Okay, so keeping that in mind, let's go ahead and build out the code. So let me just close these expos because who knows how long this quarantine is going to go. I can't dry them off. Can't afford to dry them out. Okay, so let's screen share and try to code out this idea of what we're talking about. That's another project. Okay, so we have this has cycle. So the first thing we're going to do is we can set this runner and this walker. So let's create these two variables. So we're going to have a walker, and our walker is going to start off at our head, and so will our runner, which will be our head. Now we have a check. So we care about while we have this runner, while runner, but because our runner is going to take two steps, so we're going to have to say dot runner dot next dot next. We also care about our runner dot next because we won't be able to call next on nil. So if runner dot next was nil, we wouldn't be able to call runner dot next dot next. Nil being null. Sorry, I watched those videos the other day. Now I'm thinking in Ruby. Okay, so now we've got our runners. So let's go ahead and let them move, right? So we'll go ahead and say walker equals walker dot next, and our runner will equal runner dot next dot next. Now, if they happen to be the same, so if walker is equal to runner, then we know that there is a cycle, and we can go ahead and return our true. Otherwise, eventually there won't be a runner because they'll have left, right? Because it will eventually have pointed to null. So if runner ever is null, there can't be a cycle. So after a while loop, we can just go ahead and return false. So let's give this a go. We'll click submit, and it works. Any questions on how we coded that one out?
So we never really needed the position.
No, they don't have positions. I mean, they do, but remember, linked lists don't have an indice. That's one of the negatives, I guess you could say.
Yeah, because we were like confused because An example one, you see how they have these two variables that are pointing to things. As soon as we
Yes.
saw the position one, that destroyed us.
So
That-
I would completely ignore this position. But yes, that is weird that they have that there. Why do they have that there?
That's what really got us lost, because we didn't know where that fit into the problem.
This is where the cycle exists. Position 1, this is the starting node of the cycle. This is position 0, is the starting node of the cycle. This is -1 because there is no cycle. That's what the position looks like it is. Jenya, sorry, you had something?
No, I was just gonna say to Marvin, like you always have that pre-written name of the function and the arguments they're given. Like that's it. Like these are the arguments you're given. You're only given the head. That's it. Like there is no pointer. There is no position as a second argument. So you're like, okay, then I don't need to look at the position.
All right, cool. Because I got super confused at that.
It said here, position represents the position in the linked list where the tail connects to. Yeah, so it connects to a 2 here, which is if indices 1 here, but just, yeah, it's not 100% clear. I'm totally with you on that. Those types of little confusions will get better with practice, because like a lot of them are written like that, even though they're a little bit not straightforward. It's surprisingly hard to make a more straightforward way of saying that. All right, let's look at our notes here. Ooh, okay, I'm pumped up about this one. So I've gone ahead and created a tree for us, which I will be sharing here. This is a binary tree. Let me just copy this. Okay, so I'm gonna put, this is coming in on Slack. Acting slow. No. Sorry. It does not. It is not my fault, right? That's like how that old Apple sound used to be. All right, so I will create this code snippet. This is a binary tree node, and then I have created a connection of nodes that should be represented in. It will look somewhat like that visual, where 6 is the root, 1, 3, 7, 9 are the leaves. I want you to. Your task is to print the numbers in numerical order, right? You can put them in an array if you want for bonus. Otherwise, just console log. I should say it should print 1, 2, 3, 4, 5, all the way up to 11. Okay? All right, we will do this over the next 10 minutes. All right. And here we go. Whoops, my bad. This is in order traversal. Okay, you ready for your next one? I didn't have a chance yet to try it, but hopefully it will work. Which is essentially, instead of having these, I want you to instead use this pattern in hopes that our tree should look like this. Maybe you can see where I'm going with this. 8, sorry, I know. 9, 10, oops. And 11, okay? So I'm gonna share this in here. And it's the exact same problem. I want you to print these in numerical order. Your root being A, I think. Let me just share so you don't have to build the tree. Okay, questions? All right, rock and roll. See you all in another 10 minutes. Bye. Recording. Got it. Okay, we will jump on over to this problem here. So if we're looking at this kind of tree, and we know we want to print 1 and then 2, 3, 4, where should our mind be at?
BFS.
That's right? We got to look at BFS because BFS is what allows us to go layer by layer. BFS is what you use a lot when you're looking for shortest distance problems for paths, like shortest distance between 2 nodes or stuff. It's often a BFS. So let's go ahead and start with our BFS. We'll start with our root. And in the event that we're not given a root, let's just also have a protection. So if we're not given a root, what would we want to return?
Nada.
Nada. Into it. Bueno. Right? We want to return nothing. Absolutely nothing. Sing it again now. And then otherwise, when we're thinking of BFS, what is the data structure that we use for BFS?
Q.
Yeah, right. We're going to use a queue. Right. So when we're doing recursive problems or DFS, it's a stack. You're just using the stack frames that JavaScript naturally gives us when it creates a new function call. But since BFS is iterative, we'll use a queue. So let's go ahead and make that queue. So I'm just going to call it a queue and pass in my root. And then we'll say, hey, while our queue is not empty, we're not done, right? So we'll say while our queue has a length, let's process it. So first thing we're going to do is dequeue. So we'll get let current node equal our queue.shift, right? Otherwise, and so now we've got this node, we can process it in some way, and then we have to put whichever children it has available to us. So in this one, what's our process?
We need to push it into like an output of some sort.
Sure, we could put it in an array, or we could just console log. It's so much cleaner with an array, so I'm just going to do that. But yeah, so let's keep it, put it in our output. So we'll just do our output.push, and we'll go ahead and pass our current node.value in there. Otherwise,
hey, baby, let's talk about you.
What was that?
Oh no.
Taking over from the 99 to the 2000s. Heard you.
That was pretty Ricky.
Oh my god.
Shit, is that your ringtone?
Oh my god, pretty.
Somebody was having a moment.
Okay.
I respect it.
That's fire.
Interesting. All right. Well, let's continue. We don't have rights to that song, so hopefully YouTube doesn't care. But anyway, let's keep going. Right, so we got to check which children it has in order so that we can process those as well. So we'll put in our left children, and then we'll put in our right. So if our, oh, I'm in the wrong area. I'm writing in the chat for some reason. So if our current node has a left, let's go ahead and push that in to our queue. And same with if it has a right, we can go ahead and push in the right. All right, and then whenever we finally break out of this, we can go ahead and return our output. So let's go ahead and try this. So we'll console log whatever we get back from our BFS and pass in our A node. and we see we get our 1 through 11. So looks like it works. Any questions on this?
Corey, why do we have an output and then we're also pushing into the queue?
Yeah, great. So the output is what we want to return at the end of the function, because we want all this array of all these things in order. Our queue is what's allowing us to do the BFS. So the first thing in there is the 1, and we push in the 1's value into the output. And then we're checking the 1's left child and the 1's right child, and we're pushing those into the queue so that then their 2 can be dequeued on line 103, and we can push in the 2's value, and then we can push in its children, 4, 5. So then our queue will have 3, 4, 5 in it. And then after 3 gets processed, it will push its children in. So then in the queue will be 4, 5, 6, 7. So it's how we actually do the search. It's going to keep going layer by layer like that by looking at its children.
Okay.
So these, don't conflate these. These are doing two different things. Output is just here because we're wanting an output of array of values, but it's the queue that's really allowing us to move through it.
Sorry, can you go over that? Can you like go over how it just went through it again, real quick?
Yeah. Okay.
Like the visual aspect of it from 1 to 2.
Yep, I can. I'll do it on a whiteboard. So, okay, so we've got this tree here. We've got our 1, 2, our 3, and we'll say 4 and 5. That will be good enough. And we've got this queue, and our queue starts with our 1 inside. This is not connected, right? This is just the queue has just this 1 node inside. So we're on this layer, and we're processing this node in some way, right? We've dequeued. First move is we dequeue in the while loop, and we're processing it. So in this case, we're pushing its value into the output. And then we're looking, does it have a left child? It does. So that's going to get added to the queue. And does it have a right child? It does. So that's going to get added to the queue. So now we're on the second layer. Right? Then we dequeue our 2, because that's the current node we're on. Right? So we've dequeued our 2. We've processed it, so we've pushed its value into the output. And then we've said, okay, does 2 have a left child? It does, so it's got a 4. And does it have a right child? And we go, yeah, it does. So we push those both into the queue. So now we have our 3, 4, 5. We're still processing this top layer, although you can see that we're already going to get in the order of all of them. So then we dequeue our 3. And we process it by pushing its value into the output. And then we say, okay, does 3 have any left children? No. Does 3 have any right children? No. So we'll continue to the next loop of our while loop. Then we have our 4. That's going to get dequeued. And we process that 4. And then we're going to look, does the 4 have a left child? No. Does the 4 have a right child? No. Okay. Then we're going to continue on the while loop, because we still have something in the queue. We've got our 5. Our 5 gets dequeued. We process that 5, pushing it into the output. And then we're going to look, does it have any left children? No. Does it have any right children? No. And we are done. And we return our output, or we do whatever we wanted to do with that.
Perfect. Thank you.
You're welcome. Okay. All right, let's do, I think we got time for one more problem. Gonna amp up the stakes. I'm gonna amp up the stakes. This is one of my favorite problems. So it won't be on the test, but I will tell you that when I was interviewing for my first job search, I was asked this from 2 different companies. So It's a good problem. And that is, I want you to write a function that takes in a multi-dimension, I can't spell, I'm sorry, dimensional array and returns a flat array. Okay, this should, I want this done, do it recursively. I mean, you can do it iteratively if you want. I don't want you to use the flat map or flat that exists now in JavaScript.
What's a flat array?
Okay, so let me just share my screen.
Basically one dimensional, right?
Right, one dimension. So if I have an array here, let array, and I have this 2, and this is 3, and this is 4, and this is 5, and 6, and 7, and 8, and 9. I want to call flatten on this and get back an array that looks like this. Well, yeah. Without all the weird spacing, obviously.
Hi, Grandma.
Hey, Grandma. Grandma! How you doing?
What's up, Grandma?
Grandma.
Yes.
Grandma.
Abuelita. Oh, sorry, guys.
Hello.
No, it's okay. Hey, Grandma.
Hey, Grandma, what's up?
I have some Christmas requests. All right, and here's a nested array for you to play around with. Okay, so that's the problem. I'm gonna give everybody 20 minutes. Don't look it up, right? Work on it for 20 minutes, solve it, play with it. Okay? It's a great problem. I was given it twice in a real interview. So it might not be on the test, but you might see it in an interview. All right, let's do it. We will do 20 minutes here. And adios. Hey, Ohidur, I see you're unassigned to a room. Which room were you in?
I think it was 3. It was Rafid, Desha, and Uwawaski.
Oh, Ujwakabasi. Yeah, that's 4. Okay, I got you.
Yeah, my
Index. We check to see if it has, and if it has a length property, we do something, and then.
Yeah, it's got hard to hear you for some reason. What'd you say?
Or we can show you what we did. If that's okay.
Yeah, we could share the screen.
If that's okay with you.
Yeah, share the screen. Talk me through it. Let's do it.
It'll probably be better to like visualize it. So this is where we are. So
This is Danny's in this group too?
Yeah, this is Danny, me, Giovanni.
Yeah, but we were trying to do it recursively though.
Oh yeah, right. So sorry.
That's
sorry.
okay. I'm happy. You'll like when you see the answer. Okay.
Sorry to cut you off, Danny. What were you saying about the iterative thing?
Well, it's kind of like exactly like how this is, but I was thinking about it like if we're iterating through the array, we check to see if we shift the element, we check to see if the element has a length, and if it does have a length, then we do something else, and then we continue that way somehow, some way.
So
That's what I'm thinking about it.
Yeah, but how? What's that way for if that element's got that length?
And also, what if it's an empty array?
Yeah. So yeah, I guess we were just hoping. We were hoping that if it's empty, then it wouldn't necessarily have a length, but empty arrays also. So.
We do something.
Something,
okay.
Yeah. So we wanted to pretty much call it
interesting.
If it's an array.
Yeah.
Into the loop, you know.
And I'm hearing like a little bit of recursive hate. Yeah,
hate at its finest.
but I will say that if you really hate doing something recursively, then definitely you should solve it iteratively first, and then it's usually relatively easy to adapt it to be recursive. I
just can't see it sometimes.
I would bet you that this problem is quite a bit harder iteratively.
It seems that way.
But we will see. I think it's harder than you think.
Were we in the ballpark? Like, we were really racking up.
Yeah.
Okay.
You're in the ballpark, but you're definitely missing some crucial features.
Okay. Cool. All right.
What else? How else did we do? Other groups. What did we get hung up on?
Yes, when we were working on it, like we were thinking about like all right, so basically that whole push thing we were gonna do, but it was more going through the array and seeing if the array has an array in it. Like if it is an array, then you can push that into the empty array, and then you're gonna have now you just separate all your arrays, and then you can use the concat method to just combine it into one array. We just never got a chance to like code that because we just didn't know how to.
But what about when they're if it's nested more than just it's really deep?
That's what I was thinking. Well, one of them we did code where we tried doing like two loops, but it just didn't work out.
Okay. Yeah, this is a tricky one. What else? Any other? I love hearing about
You got this right at the interview?
I got it at 2 different interviews.
And you got it in both of them?
Yeah, I knew this problem.
Oh, that's awesome.
Although I wrote it in about 10 minutes on the first one, but I wasn't familiar with the coding environment, so it needed me to console log the answer, and so nothing was showing up when I would run it. And I spent 40 minutes debugging code that didn't have a bug, and the interviewer didn't realize it for some reason until the end. And we finally was like, oh, I just wasn't calling it with a log. That's why we didn't see it. It works. And then, and that was a big negative. But the next time I got it, I did it in, the same time, 5-10 minutes. And then I knew that if I was going to call it, I would just invoke it with a console log in there so that we can see it. Neither here nor there. Anyway, let's go over this one. I really like this problem. So we have a flatten function that we need to write, right? So let's go ahead and start with flatten. Everybody can see my screen, yes? No, yes, no, maybe?
Yes.
Oh, okay, great. Thank you. Thank you very much. Okay, so we've got flatten, right? This is taking in some sort of an array. There we go. So this is kind of a cool problem because you solve this iteratively and recursively at the same time. But it's still technically recursive because it's a recursive because you are calling itself. But you don't really have the strict base case. So it's like a slightly different feel. Some of you may have gotten a problem similar to this in the technical feedback fair. I'm not sure if you did. But there was a problem that's almost the same as this. Which maybe we'll do another day. But, okay, so we have our output that we want, and we are going to iterate through this array because we have to touch each element, right? So we can say for array.forEach. Oh, that's weird. Okay, for each, we have an element. And then we have to check, because what do we care about within this element? What matters?
Whether or not it's an array or not.
Definitely. So is there a good way for us to check if an element is an array?
Has a length greater than 1.
Strings could have
array.
That.
Array.
Doug, a man after my heart, right? Array.isArray. So we could say, hey, if array.isArray, and it takes in an element. So this is going to return true or false depending on if this element is in fact an array. So if this is an array, then otherwise there's like a few things you would have to do. You would have to check if it's an instance of object, but it also has a length property and it's not null or something. There's like a few, it's like kind of a weird thing. But luckily this method exists in JavaScript, so it keeps it kind of easy. And so if this is an array, we want to go dive into this array, right? We want to do something. We want to flatten this array as well. But we want to store this flattened array inside of our output. But this is going to give us an array. So we can't just push it into the output because then we'll end up with a multidimensional array again. So instead, we have to say output equals output dot concat. We can concat it. And so it will merge whatever array we get back from this into this array. Else, we just have a regular object. So, or a regular element. So in that case, we can just go ahead and push in the element. At the very end, we can go ahead and return our output.
That's so much cleaner than I thought it was going to be.
Oh yeah, just wait, we're gonna refactor it. But so we've got this, so then let's go ahead and try it. So console.log, don't forget that, or you might debug correct code for 40 minutes. Write flatten, and we will try, I'm not bitter about that, and we'll try array, and let's go ahead and give it a shot, and we get our multidimensional array, our flat array. Okay, any questions on this?
Yeah, Corey, would you mind just going over that line 121 again, exactly how that, because like I'm not seeing the array for each, like exactly how that method is working on this. I'm just not grasping it right now.
Sure. So what does our flatten method return?
It's returning an array.
Yeah, exactly, right? It's always returning an array.
Right.
And so we need to update our output in some way based off of this element, because we need all the elements. Like when we hit this array, we need all these elements, 3, 4, 5, 6, 7, right? So we need all these. So we have to call flatten on this little array here, which we'll call flatten on this array, which will then call flatten on this array. And so this array is going to end up returning just an empty array, right? We can think of if this was our whole project.
So then it's going to push all those arrays that you use with, because the flatten, calling flatten kind of calls each array by itself, and then you're concatenating all those arrays into one array.
Exactly. See, because if we didn't have concat here and then we instead use like a push, we'd just end up pushing an array back in to our output. So we would, if I change this to push, you'll see. I think we'll end up with like an identical result. Oh no, it freaked out. Why did it freak out? Oh, just otherwise it becomes right. It just becomes an identical result.
Okay.
Anybody know? Can anybody tell me why this broke when I did it like that instead?
Reassigning.
Yeah, but reassigning works fine right here. How come it didn't work when I had push?
Run it again so I can see it break.
Okay.
Is it because you're mutating? No. You're changing on it's like changing on change.
No.
Are you trying to push that
At some
function
point,
before it gets
something is
invoked or
not.
something?
No, it gets invoked. Yeah,
Output
so
is
something.
changing.
So
Output is not an array. The output is not an array, right?
What is output?
Output, I don't know, but if you can't push it, then it's not an array.
Okay, I'm with you on that. Who can tell me what output becomes?
It becomes a number.
That's right. Because who said that?
Because J.
John?
Jones.
Yeah. How come?
Yeah, because from your array, like if it's not an array, then it's gonna just like push that number into your
No,
output.
the result of push is a number, like the return value.
And so that makes output a number because of that
At
return
some
value.
point.
Yeah.
Right.
And that's why
Exactly.
push is no longer a function. I get
So
it.
every time we use push, remember push evaluates to the new length of the array. So if I did this, then our output would be the length of the array, and then later on we're trying to push into a number. So that's why that wouldn't work. But regardless, it should be concat, or we could have used the spread operator of some sort, right? So let's write this with reduce, right? So with reduce, it's the same kind of logic, right? It's just going to be const. We'll have our flatten, takes in an array, but then our reduce can do all this stuff for us, right? Our reduce can keep track of this output for us. So we can just go ahead and return array.reduce. It's going to take in our accumulator and our element. And our argument that will pass it is its empty array, right? So this is, personally, this is probably the better answer for in your job because it's more readable. But, you know, nothing's too wrong with reduce, but then it's the same logic here, right? We can just basically steal the logic. I don't know why it auto-formatted like that. Horrible. Right, and instead, ugh, it was like really, what a horrible copy. Better to just have written it from scratch. Okay, right, so our array, if our element is there, instead of it being output, these should all be our accumulator. And then at the end of each one here, we can just go ahead and return our accumulator. I believe that will also work. Nope, it broke. Let's start debugging. Okay, so part of the issue could be that we wrote this in an ugly way because of the copy and pasting. There we go. So it still works. If you really wanted to go crazy with shortness, right, you could make this like a ternary as well. But and then you have just like one line in here. But it's even less readable. So we're going to leave it with this. Actually, yeah, we could just say return. Like if we really wanted to play golf, we could do like ACC flatten element. And this would be, this is not good though. And maybe somebody can tell me why this is not good. Can anybody tell me what's wrong with this code? It will work. So it works, but what's wrong with this code?
Is the mutation that is going on in there?
So there's no mutations happening here. I can prove that by console logging our original array underneath. Right, mutation has to have a mutating operator, so like a push, a splice, a pop. What else might be wrong? What's the time complexity of this?
Linear.
So I heard somebody whisper linear. So it looks like that. That is it? What do you think the time of the spread operator is?
Is it constant? Because you're just
so what's it do?
It's also linear because it loops through and deconstructs it, adding it to what you have.
Exactly, right? So it has to still loop through and make a copy. So in order to copy, this is also linear. So all of a sudden, this has become quadratic. Yeah, I was making sure I was recording because we're iterating through this array, but then we're iterating through this again. So like, yeah, it looks cool, right? And we could really make this like crazy short, right? But it's not the most time complex. So if it's the problem of how do you write the most confusing short code that might appear kind of cool, then this is a really good answer. But if you want an efficient code that's readable and all that, right? Because this still works. You should stick with this one. This is way more readable. What's going on? It's got better time efficiency, even though concat still is making a copy and going over. I think yes. Okay, but this is how we can write flat. I'll comment on this one because it's the cleaner approach. This is for people who like to play golf. Right? We could also do implicit returns if you really want to go crazy. Then we don't need anything. Just okay. Anyway.
That's
What? Yeah, it's how you write it in one line, essentially. But one line doesn't mean everything, right? You want really readable code. It's technically this is nicer. All right. Any questions on any of that? Okay. Great job, everybody.